So in class today we talked about what happens when compounds are dissolved in water, and if we can test if they conduct electricity. We learned how to classify those compounds into 3 different groups: strong electrolytes, weak electrolytes, and non-electrolytes. We're going to continue that discussion by just reviewing acids and bases, because they also fall into the same category. So really briefly, remember we can quantify any compound as an acid or a base. And the main way we do this is by using something called the pH scale. Okay, the pH scale, we're going to learn how to quantify it later in this unit. But we did learn, and this should be familiar to you last year, if a compound has a pH between 0 and 7, we call it an acid. It's acidic. We also know that they taste sour, that they burn skin, and that they turn pH paper or litmus paper red. It's a very easy way to tell if a solution is an acid. And there's some common examples: lemon juice, apple juice, bananas, vinegar, tomato. Those are all pHs of 3 to 4. They're all considered acids. However, if a solution has a pH between 7 and 14, we call that substance a base. And bases taste bitter, base bitter. They turn pH paper blue, and they tend to have a slippery texture. Think of soap. Soap is a basic compound. Now, don't get caught up on the slippery and burn, because bases can also corrode your skin. They can cause really bad burns. But the other portions and descriptions of acids and bases should be reviewed. If a substance has a pH of 7, we call it a neutral compound. Another term you need to be familiar with bases, okay? Bases are often also referred to as alkaline substances. Alkaline substances. If something is alkali or alkaline, that is another word for something that's basic. So you need to be familiar with that term as well. We learned that there are a couple different definitions molecularly. Up here, this is what we see at a macroscopic level, at a big scale. What does it taste like? What is this number on the pH scale, etc.? What is actually happening on the molecular level? And last year we learned about the Bronsted-Lowry definition. We're also going to revisit Arrhenius and Lewis acids and bases later. But we learned that a Bronsted-Lowry acid, according to the Bronsted-Lowry definition, is a proton donor. It gives up H pluses. Whereas a Bronsted-Lowry base is a substance that accepts H+. It's an H+ or hydrogen ion acceptor. So we learned how to identify which is which using a balanced equation. Now, one thing I just want to point out here, this A should be an arrow. The formatting got a little messed up when I copied this over on both of these. Okay? But if we're given this equation, if we take H2SO4 and we drop it in water, without looking at its conductivity, how can we figure out if it's an acid or a base? Well, according to the reaction here, all we have to figure out is H2SO4 an H+ donor, a hydrogen ion donor, or a hydrogen ion acceptor? So, well, all we have to do is track it. Well, here we're starting with 2 H+. We've got to follow the same compound, follow the polyatomic anion, SO4, SO4 sulfate, to the product side. We see it just has 1 H now. So since H2SO4 lost a hydrogen ion, we would call it an acid. And you could then test that with pH paper to determine, is its pH less than 7? Does that agree with what you would expect? We can do the same thing with H2O. We see that H2O has 2 hydrogens here. If we track it over, it now has 3. So since it gained a hydrogen ion, it accepted a hydrogen ion, we would call H2O a base, according to the Bronsted-Lowry definition. Let's look at another example right below. You can try it on your own if you want, or just watch along with the video. So, Nh3 Ammonia. Is that an acid or a base? Well, if we drop it in water, the products we get are NH4 plus, ammonium ion, and OH minus, a hydroxide ion. Well, according to the Bronsted-Lowry definition, we have to figure out, is the hydrogen ion getting donated or accepted for ammonia, NH3? Well, let's track it. NH3 starts with 3 hydrogens. The compound down here has 4. So since it gained a hydrogen ion, it accepted a hydrogen ion, NH3 is going to be a base in this particular reaction. And I know I wrote it in red, but don't worry about the color at this point. Water, in this reaction, has 2 hydrogens. It ends up with 1, so it lost. It went from 2 down to 1, so it lost. It donated a hydrogen ion, so in this reaction, H2O is acting as an acid. And remember, water is powerful. Water can act as both an acid and a base. And the word that we use for a substance that can do that is amphoteric. A good vocabulary word that we need to know, amphoteric, a substance that can act as a base and an acid. Another thing you might remember is if you see hydroxide ions in solution, this is a dead giveaway that something is going to behave as a base. That's not according to the Bronsted-Lowry definition, but it is something to be aware of. And on the flip side, if you see an H3O+, which we need to know is called a hydronium ion, this is all one word, I'm just running out of space, hydronium ion, that is automatically going to be an acid. If you drop a substance in solution in water and it makes H3O+, boom, acid automatically. So, how does this connect to what we learned today? Well, there's differences between acids and bases. Some acids are strong, some bases are strong, some acids are weak, some bases are weak. And this kind of corresponds to how they behave electrolytically. Are they strong or weak electrolytes? Well, here's a molecular model of what's happening with a strong acid and a weak acid when it's dropped into solution. So we can see an acid over here has a white sphere and a red sphere. The white sphere represents a proton, an H+, and the red sphere represents a negative ion, any negative. We'll just say A negative, anything. When the strong acid, the molecules are all starting together, is dropped into water, notice what happens to those molecules. In solution, none of those molecules are still together. The white protons and the red negative anions are all separated. Or the vocabulary word, we would say this solution is completely dissociated. So dissociation, if something dissociates, that means break apart. Since it's completely dissociated, that means that all of the molecules, all of these acidic molecules, broke apart into their positive protons and negative anions. Since they all broke apart, they all dissociated, this has to be a strong acid. On the other hand, if we take a solution that's considered a weak acid, the way we can tell at the molecular level is those same molecules that started bonded together, some of them will dissociate. You notice here we have a proton floating around, and here we have an anion, red sphere floating around. But we also still have some molecules that are still bonded together. So we kind of have a mixture. We have some molecules that are dissociated, and we have some that aren't. So we would say this is only partially, and again this should be review, partially dissociated. Weak acids only partially dissociate, which means only some of the acid molecules break apart. I could have easily changed the word acid here to base. It doesn't matter. Okay? They do the same thing. A weak base only partially dissociates. A weak acid only partially dissociates. However, there is a few more things you do have to memorize. There are 6 strong acids, and you have to know the names of them. Besides all of our other nomenclature, these are the 6 strong acids. They are HCl, hydrochloric acid, HNO3, otherwise known as nitric acid, H2SO4, otherwise known as sulfuric acid, HBr, hydrobromic acid, HI, hydroiodic acid, sometimes also known as hydriotic, but just stick to hydroiodic for now. And the last but not least, HClO4, chloric acid. You have to have these 6 strong acids and their names memorized, because these are the only strong acids that completely dissociate. We'll learn later how to compare the relative acidities of compounds based on their structure, which is really powerful, but for now you just got to have these 6 strong acids memorized. The other thing you need to know is, since strong acids and strong bases completely dissociate, they have ions, positive and negative, floating around. So strong and weak bases, strong acids and strong bases are all strong electrolytes, because they have more ions floating around that can transfer electrons. Lytes, ran out of room, electrolytes. Weak acids and weak bases are only weak electrolytes, and we'll learn about some organic acids and organic molecules that would be considered non-electrolytes. But for now, this connects back to what we learned today in class and what you need to have going forward. Take a minute to summarize any key vocabulary words, write them down in a corner on your notes, and also generate one question that you have about the material. The big focus that we're going to cover this unit and today is the molecular models. How do we represent acids and bases using molecular models like these?